Hello everyone, welcome to another episode of Elementary Maths with Solid Club. My name is Akin Loco. Our topic for today is matrices. So let's dive in. I'll try to be as brief as possible. A matrix is a rectangular array of numbers or symbols arranged in rows and columns. If a matrix has m rows, for instance, and n columns, then its order or dimension is m by n. For example, we have a 2 by 3 matrix on the screen labeled matrix A. You can see the elements of that matrix 1, 2, 3, 4, 5, 6. It's 2 by 3 because we have 2 rows, 1, 2, 3 are on row 1, 4, 5, 6 are on row 2, and then we have 3 columns. 1, 4 is on column 1, 2, 5 is on column 2, and 3, 6 is on column 3. Matrices are useful for organizing data, performing algebraic operations efficiently, and solving systems of linear equations systematically. Let's see some basic definitions regarding matrices. An element or entry of a matrix is any individual number inside the matrix. The entry in row I and column J is denoted by A subscript ij, right? It's just like a terminology to be able to locate or identify elements or entries in our matrix. So if I have a subscript 1, 2, for instance, I go to row 1, column 2. This is row 1, this is column 2. So for this matrix A, for instance, A12 will be 2, elements 2. Another definition, a matrix with exactly one row is called a row matrix or row vector. A matrix with exactly one column is called a column matrix or column vector. Just like we can see down here, this is a column matrix and this is a row matrix. That's just one row. Next one is square matrix. It's a matrix with the same number of rows and columns. That is, the order is now n by n or m by m because the number of rows and columns are equal. A zero matrix is a matrix in which every entry is 0, like you can see here. Now, types of matrices. A diagonal matrix is a square matrix, first of all, in which all entries outside the main diagonal are zeros. For example, look at this matrix down here. Every other entry is 0 apart from entries on this main diagonal. So that qualifies this matrix as a diagonal matrix. A scalar matrix, another definition, is a diagonal matrix in which all diagonal entries are 0. All diagonal entries are 0 for a scalar matrix. So it's just like the opposite of diagonal matrix. For a scalar matrix, all these diagonal entries will be 0, right? Sorry, all diagonal entries are equal. to be a diagonal matrix, every other entry will be 0 apart from entries on the diagonal, but then all the entries on the diagonal must be equal. Like this identity matrix, we are coming to that, but it is also a scalar matrix because you can see all the elements on the main diagonal are the same thing, they are 1 1 1. The identity matrix is a scalar matrix with diagonal entries equal to 1. It acts like the number 1 in matrix multiplication. In multiplication of usual numbers, normal real numbers or integers, if you multiply any number by 1, you get the number back. Same thing for matrices. You multiply any matrix by the corresponding identity matrix that is of the same order, you get back that matrix. That's what they're saying with all these equations right here. And this is an example of identity matrix. For a scalar matrix, you can have the major diagonal entries to be 2 2 2, for instance. But for identity matrix, the main diagonal entries must be 1 1 1. It must be 1, and then the matrix must be a diagonal matrix. A transpose of a matrix A, written this way, A raised to power T, is obtained by interchanging rows and columns. If a matrix A is equal to this, you are denoting the elements of the matrix as Aij, then A transpose will automatically be Aj, to define the entries inside A transpose, because we said we have interchanged row elements with column elements. Another definition, a square matrix A is called symmetric if A transpose is equal to A. That is, if a matrix A is equal to its transpose, then that matrix is symmetric. A square matrix is called upper triangular if all entries below the main diagonal are 0. And then is lower triangular if all the entries above the main diagonal are 0. So we can see examples. This is a symmetric matrix because if we switch the rows for the columns, we'll have the same matrix back. You can try that out. And then this is upper triangular because you can see below the main diagonal all entries are 0. Yeah, this is lower triangular because above the main diagonal all entries are 0. And we have this matrix, for example, if we want to find the transpose 1 2 3 4 5 6, our row 1 becomes our column 1 and our row 2 becomes our column 2, and so this is A transpose at the end of the day. If you do that for this matrix, you see you get the same thing back for this symmetric matrix. Augmented matrix for linear systems. I'll try to rush through this one. If we have a system of linear equations, this is what we mean by system of linear equations. That is an array of linear equations, more than one linear equation. So this particular example we're seeing here, we have 3 linear equations working together as a system. They depend on one another, and then it implies that the variables in each of them are linked to one another, right? So we have 3 variables in this system, x, y, z, and 3 equations, right? right? So let's see the definition. A system of linear equations can be represented by an augmented matrix which records the coefficients of the variables together with the constant on the right hand side. So this is just it. This is the augmented matrix for this system. By taking the coefficients attached to each of the variables in each of the equations. So for equation 1 will represent our row 1 in our augmented matrix. What is the coefficient of our first variable? X is 1. Second coefficient for y is -2, and for z 3. The constant on the right hand side, as we read in the definition for augmented matrix, will be on the other side 9, and you separate with this vertical line like that. But you take note, in your system the variables must be arranged in the same order all through: x, y, z. X, y, no z element here, so we'll have 0 for z. You can see 0. So it must be arranged x, y, z before you can generate an accurate augmented matrix. Matrix algebra. Matrix addition and subtraction. Two matrices can be added or subtracted only when they have the same order. Take note, the operation is performed n3 by n3. For example, we have matrix A 1 2 3 4, matrix B with entries 5 6 7 8. A plus B will be our element on row 1 column 1 for matrix A plus our element on row 1 column 1 for matrix B. So each element will take its corresponding element in the next matrix and perform the operation. If it's addition, you add; if it's subtraction, you subtract. So here 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8. We'll take those sums. 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 10 is 7, 4 plus 8 is 12. So this is our resulting matrix, our answer at the end of the day. A minus B similar. The operation sign just changes. Scalar multiplication. Multiplying a matrix by a scalar means multiplying every entry of the matrix by that scalar. Simple and straightforward. If I have a matrix A 1 2 3 4 and a scalar C equals 3, for instance, C multiplied by our matrix A simply means I'm multiplying that matrix A by 3, and it means we're multiplying each of the elements inside matrix A by 3, like we can see. 3 times 1, 3 times 2, 3 times 3, 3 times 4, that's 3, 6, 9, 12 at the end of the day as matrix CA. Matrix multiplication. If A is an M by N matrix and B is an N by P matrix, then the product AB is defined and will be an M by P matrix. We need to take note that we can only perform matrix multiplication on two matrices A and B if the column, which is N, the column for A is N, and the row for B is N. So the column for the first matrix you are considering must be equal to the number of rows for the second matrix you are considering, right? Then they will merge up to give you a new matrix which is M by P. That's what it's saying. If the two matrices you want to multiply don't satisfy that condition, then you cannot multiply them. The entry in row I and column J of AB is obtained by taking the dot product of row I of A with column J of B. We'll see all that in an example. Now, you need to take note that matrix multiplication is generally not commutative. That is, A times B, matrix A times matrix B is not equal to matrix B times matrix A. So the order matters. If we have these two matrices we are told to multiply, we need to check this condition in our first definition here. The order of matrix A is 2 by 2, order of matrix B is 2 by 2. So the number of columns in matrix A is 2 and the number of rows in matrix B is 2. So these two matrices can be multiplied by each other. They are conformable, right? And the resulting matrix must be 2 by 2. So how do we do the multiplication? You take your row 1 in your first matrix against your column 1 in the second matrix. Alright, so that is 1 times 5 plus 2 times 7. That gives us 19. That will give us our first element in the A in the product A times B, which is 19. That will be on the first row, first column, row 1, column 1. For row 1, column 2, this 22, you take the first row in your first matrix against the second column in your second matrix. So that will be 1 times 6 plus 2 times 8. That gives us 22. For your row 2, column 1 in your product, you take row 2 in your first matrix against column 1 in your second matrix. You can see the pattern, you can see how it's going. So that will be 3 times 5 plus 4 times 7. That gives us 43. And for your row 2, column 2 in the product AB, you take row 2 in the first matrix against column 2 in the second matrix. That will be 3 times 6 plus 4 times 8, and that gives us 50. And that's our result here. So I'll continue in the next video. Thank you.